Good evening, everybody. You're all very welcome to our Zoom this evening, where the focus will be meteors and fireballs and such like. In the second half, I'm going to invite Brian Coleman to update us on the current status of the UK Beacon project. You would have seen that next month we've got Prof. Karen Chaplin coming. Space weather, cosmic radiation, instrumentation and science. So we should be here till probably the midday the following day, I think, with that agenda. We've got something to look forward to. We're going to have an evening on using small dishes, SDRs, and interferometry. So if you've got a couple of sat dishes knocking around, as I have in fact, and haven't actually done anything with them yet, then that'd be something really good to look forward to. Anyway, this evening I'm so pleased to introduce Dr. Daly. Your name has just gone off my screen. I do apologize. Luke, yes. Without further ado, Luke, I'm going to hand over to you. You should be able to share your screen if I've set this up correctly.
Cool. So can everybody see that?
Yep.
Yeah, that's good.
Looks good to me.
Is there a little floating head in the way, or are we good? Is like this thing up here blocking everything, or?
No, I can't see a floating head.
Okay. I'm just going to hide the video panel and the meeting controls. Cool. Hopefully that's all good. Yeah. Thanks so much for having me. It's really great to come speak to you all. Yeah, my name's Luke Daly. I'm a lecturer at the University of Glasgow in the School of Geographical and Earth Science. And I have been kind of in and out involved with fireballs and meteors through the lens of wanting to get my hands on meteorites. So my expertise is studying space rocks from Mars, from asteroids, tearing them apart at an atomic molecular level to figure out what they can tell us about how our solar system formed. And so this talk is really going to be about that kind of journey with Fireball Camera Observatory, starting in Australia, coming to the UK with the UKFAll Alliance, and then our kind of recent, relatively recent, it's like nearly 2 years ago now, the success of finding the first UK meteorite in 30 years. And some things where we can kind of look forward to about what we want to do next. So, like I said, I'm a planetary scientist, and what that basically means is we're interested in some of the big questions in our solar system, and that can involve, how does our solar system form in the first place? How do you go from like a big ball of gas and dust, collapse that down under gravity, so the center gets so hot and under such pressure that nuclear fusion starts, so you get a star? How does the swirling disk of gas and dust around that young sun coalesce to form asteroids and eventually planets and the planetary system that we see today? And then the really important question at the end of all that is, how do we get a third rock from the sun that is habitable, on which life could emerge? And then that life eventually becomes arguably intelligent, that can start trying to figure all these questions out. In that, another big question is, where did Earth get its water from in the first place? And that is a very key question for the origin of life, because life as we know it needs water. And in our solar system, where in that sort of young, energetic, protoplanetary disk of gas and dust, that young, energetic sun in the center is kicking out a lot of heat. And that produces what we call the snow line. It's basically a plane in the disk, inside of which water is in the vapor phase, and outside of which water is in the ice phase. So it's solid. And that young, energetic sun blows those vaporous clouds of water into the outer solar system, and we lose it from the inner solar system. And so what that means for the poor Earth is Earth formed inside that snow line and should have formed relatively dry. Now, I live in Glasgow. That's clearly not the case anymore. Something must have changed. It rains here all the time. And so something's got to happen between now and then to deliver that water. And that's one of the kind of key questions is where did Earth's water come from in space, and what are the delivery mechanisms? We can start addressing some of these questions in a variety of ways. We can use telescopes to look out into our galaxy at forming protoplanetary disks. This is an image of a protoplanetary disk side-on that's forming in our galaxy right now. It's from the ALMA telescope. And what I really love about it is you can see this kind of beautiful ring structure, which might be gravitational instabilities, but it also could be the early formation of planets clearing out their local region. And what that does, it effectively isolates different parts of the disk geochemically and spatially, so they could evolve in their own kind of way, maybe producing different meteorite types, different asteroid types, different planet types. A bit closer to home, we can use telescopes to look at the asteroid belt and the structure of the asteroid belt. This graphic is just kind of showing all the known near-Earth asteroids that have been kind of discovered over the last few decades, to the sort of like point where we get towards the present day, and we're tracking hundreds of thousands of objects. 90, I think it's like 95, 96% of everything bigger than a house up there that's anywhere in our local neighborhood. And we're getting this really interesting view of the structure of our asteroid belt, and near Earth space is clearly very, very busy. And that brings us to kind of, okay, we have all these asteroids in the asteroid belt. What are they? What are they made of? And we also have all these meteorites on Earth, which come from space. And I don't want you to worry about this figure too much. Basically, the top is the meteorite classification system of all the different meteorite types, and as you can see, it's this alphabet soup of hell. And the lower graph is the asteroid classification system based off the light spectra that we receive bouncing off the surface of those asteroids. And you can see there's lots of different types. One of the key questions we have is, how do these two graphs link together? What asteroid types are linked to what meteorites? And that has led to sample return missions, space missions, to send out probes to these asteroids, to celestial bodies, to collect material. So we had the Itokawa mission, a Hayabusa mission to the asteroid Itokawa, which is an S-type asteroid, landed on the surface, brought back a few thousand grains. The Stardust mission flew through the tail of a comet, so we can have a sample of a comet and figure out what comets are made of. There is a mission called OSIRIS-REx, which is a NASA mission that went to the asteroid Ryugu, probably collected between 1.5 kilos and 0.5 kilos of that C-type asteroid, and that will deliver that sample to Earth in September this year, so relatively soon. The Apollo missions, they went to the moon, brought back several hundred kilos of lunar rock, helping us figure out how the Earth-Moon system formed. Very recently, and sort of like one of the kind of cool things I've recently been able to work on is the Hayabusa 2 mission to the asteroid Ryugu. This is a video of it going down onto that asteroid surface to take a sample, shooting a copper bullet into the surface. Some of that dust that got kicked up went up the chute into the sample canister container, and we recovered about 4 to 5 grams of material from this asteroid. And what that basically allows us to do is go, okay, we've measured the stuff from this S-type asteroid Itokawa. What does it look like in the meteorite record? And turns out it looks very similar to an ordinary chondrite type L chondrite. So it's like the first direct link we have that, okay, S-type asteroids might be very similar to these L chondrite meteorites we have on Earth. Similarly, with Hayabusa 2 landing on Ryugu, what was really surprising is that material got brought back and it looks like something called a CI chondrite. Now, CI chondrites are incredibly rare, but C-type asteroids are one of the most abundant asteroids in the asteroid belt. CI chondrites are also really wild and weird and interesting, that they are basically like a big lump of clay. Probably the reason they're so rare on Earth, and we only have 4 of them, is they disintegrate like when you look at it. And they're interesting in 2 further ways. One is they're clay. They've been extensively altered by fluids to the point where all their original mineralogy has been changed by its interaction with that fluid. However, they are also the most chemically primitive objects we have in our solar system. So basically, if you took the hydrogen and helium out of the sun, put the rest in a blender and made a rock out of it, it would look an awful lot like a CI chondrite. So it looks like it's chemically primitive and nothing has happened to it for 4.5 billion years. But yet, it's been extensively altered by fluids that should strip certain elements out of it. So it's a kind of a bit of a conundrum, what these kind of things represent and how they altered in the way they did. And it's amazing we have this material from Hayabusa 2. And like I said, other asteroids will be coming, or other sample return missions will be coming in the near future, and hopefully will provide more of these links. However, we don't have to wait for that, and we also don't have to spend multi-billion or multi-millions of pounds to go to these asteroids and collect them. Space comes to us all the time. About 50,000 tons of material hits Earth's atmosphere every day. Some of it are these brilliant, beautiful fireball events that last several seconds that herald like the arrival of a large rocky object at the top of Earth's atmosphere. And if we're very lucky, some of that material could survive to the ground as meteorites. I'd like to, before I go on, get a bit of the kind of definitions out of the way, because I often get asked the question, what's the difference between a meteorite, a meteor, and a meteoroid? So a meteoroid is basically a rock in space. Any old rock, well, extraterrestrial rock floating around in space, nowhere near Earth, we'll call that a meteoroid. A meteor is just the light in the sky. It has nothing really to do with the rock. It's just a sort of phenomena that occurs as that rock is flying through our atmosphere. It's starting to decelerate. Friction forces of the atmosphere sort of moving past it very, very quickly as it slows down, hooks up both the atmosphere and the outer surface of that meteoroid, producing fluorescence and producing a light in the sky, which we call a meteor. So meteor is just the light. If that meteor lasts for more than like a second, we'll start calling it a fireball. And again, that typically is because it's a bigger meteoroid that's entered Earth's atmosphere. The way I kind of like to think about it is a fireball. If you see it, you can tell your mate that's sitting next to you stargazing, oh, hey, look at that. And they will also be able to see it and catch it. Whereas a meteor or a shooting star, probably a sand-sized particle, it's one of those things where you blink and you miss it. It doesn't last very long, doesn't go very far. And then right at the end, we have meteorites. Now, meteorites are basically a meteoroid, but now it's on Earth. And it undergoes a mystical, magical transformation where nothing actually materially changes in the rock, apart from it's now on Earth. So it's just a kind of function of definitions that we call meteoroids, space rocks in space. And as soon as that space rock hits the Earth, we'll call it a meteorite. We have lots of different types of meteorites, and they all tell us wonderful things about how our solar system formed. So there are kind of three main groups. There are iron meteorites, which have a really imaginative name because they're made out of iron metal. And they form or are from the cores of planets or worlds that differentiates into a core mantle crust structure. So they partially melted, all the metal rained down into the core, all the lighter stuff floated up to form the crust, very much like our Earth, like our moon. So that means iron meteorites are really wonderful to study because they are basically samples of planetary cores. Some poor planet early in our solar system got busted up to such a degree that it exposed the core and fragmented it, and fragments of that core now rain down on us as the iron meteorites. And so not only can we then use that to understand the cores of other planets, but we can also use it to understand what our own Earth's core might look like and what it might be made of, because we can't get samples of our Earth's core because it's really dark and deep and squishy and hot and miserable down there. We can't drill that deep. So it's great that we have these meteorites as like a proxy for Earth's core. We also have the stony iron meteorites. They are imaginatively named because they're made of stone and iron metal. So they're basically these beautiful patchworks of metal with embedded silicates, like this beautiful green mineral called olivine. We used to think that they came from the core mantle boundary of planets that are differentiated, but recent magnetic measurements by people like Claire Nichols has shown a really interesting thing that they might actually sort of be remnants of some of the most cataclysmic events in our solar system, where two planets collide into each other and the core of one planet merges with the upper mantle of another planet, producing this beautiful patchwork texture. And then finally, the meteorites that I spend most of my time studying are the stony meteorites. They are imaginatively named because they're made out of stones. There are the achondrites. There's two groups. There's the achondrites. They are from the surfaces of differentiated worlds, from the crust of differentiated worlds like the moon, like Mars, like Vesta. And so they're typically samples of volcanic rocks, so we can understand volcanism on other planets, or impactite rocks, so rocks formed by asteroid impacts into the planetary surface, so we can understand impact processes across the solar system. And then finally, we have the chondrites, which is kind of my favorite one. They are basically all the minerals and all the grains inside them formed in the first few million years of our solar system's history, before the time that there were planets, before the planets had formed and accreted. These kind of like primitive bodies were forming in the chondrites, and basically nothing happened to them for the next 4.5 billion years. So they kind of formed, and stayed the same. Some of them went into as the building blocks of planets, but some of them survived that process and provide a window into what our solar system was like before there were planets, and what our solar system was like when the sun first started to shine. However, these are all great, and so I should say the way we find meteorites typically, the sort of traditional method, is just get really lucky, and you can fabricate your luck a little bit. Is basically going around trying to find little black rocks, which is what meteorites typically look like, in places where little black rocks shouldn't be. And one really good place to go there is Antarctica, because little black rock on white ice is very easy for the human eye to see the contrast. And also, if you find a little black rock on the surface of an ice sheet in the middle of nowhere, it's very hard for it to get there any other way apart from falling out the sky. So typically, most objects you find at the surface of an ice sheet in Antarctica tend to be meteorites. You also have some really nice concentration mechanisms there. So this is a diagram of the glacial ice sheet. So a meteorite falls somewhere on the ice sheet, it sinks down a little bit. And as that glacier moves and it butts up against a mountain range, the surface shear winds in Antarctica ablate that ice surface and basically suck up in a kind of Hoover motion all these meteorites from depth and deposit them at the surface. And then the Antarctic Search for Meteorite, among other expeditions, goes out and finds little black rocks and bring back thousands of the things. There's also a UK-led expedition that's gone out a couple of times to try and find the missing iron meteorites. And basically through this, going to Antarctica, going to hot deserts, we've got over 60,000 meteorites in worldwide collections, which is fantastic. They're wonderful. They can tell us lovely things about our solar system, but they're all missing one key piece of information, and that is their orbit. We don't know where they came from or where they started in our solar system. We just know that at some point over the last 1,000 years, maybe, they landed on Earth. What we would really love to have is their orbital information. And this data set sort of flying around on the screen right now is all the fireballs that have been seen by the Australian Desert Fireball Network over the last kind of decade or so. There's over 1,000 fireballs in here, and you can start, they're the teal dots that are kind of coming in to hit that third rock from the sun, and you can start to see some structure. Like I think this is the Perseids or maybe the Geminids coming in to nail the planet Earth just now. And so by imaging fireballs as they come in and hopefully then collect the meteorite, we might be able to understand where these meteorites are coming from and put them in their geological context, which is incredibly, incredibly powerful for planetary science, for understanding our solar system, for understanding the geological history of planets and moons and asteroids in our local neighborhood. And this kind of, is one of the key questions and missing links in planetary science anymore. Before we can answer, are we alone in the solar system? Where did Earth's water come from? How do you form a planet? How do you form a solar system? You need to figure out where the space rocks we've got came from. And like I said, 50,000 tons of material every year hits Earth's atmosphere. And if we can image those meteors and those fireballs, we can start to figure out where mass is being delivered from in our solar system and where things are coming from. And that's where automated camera networks come in. I'm going to start with the example of the Australian Desert Fireball Network. It's in Australia. It's a continent scale camera network covering 1 million square kilometers of sky. They're these autonomous systems. They're basically an off-the-shelf digital camera with a fisheye lens that take a single exposure for 30 seconds of the night sky every night from 52 locations. A lot of work's gone into automating that because that is a lot of data. 52 cameras times 1,000 images per night is a lot of things to go through. So sort of an automated pipeline of calibrating the camera, detecting the fireball, making sure it's not a plane or a bird or something else. It's actually the fireball, figuring out what time that fireball came in to triangulate it, to check around the other cameras in the network to see if they saw it too. And then eventually what we're able to do is triangulate it and figure out if anything survived. I'll just quickly go over kind of how we do the timing sequence, because it's really clever, I think at least. And because we're taking a 30-second exposure of the night sky. And so that timing precision is good. We know it came in that 30 seconds, but we want to do better than that. And so what we do in that 30 seconds is we flash opaque and transparent the liquid crystal shutter. So it goes like dark, clear, dark, clear, dark, clear. And so if anything really fast comes across our image, like a fireball, it will be cut up into long and short dashes. And we sort of pulse the dark light, clear, dark, in a very systematic way called the De Bruijn sequence, which basically embeds a unique timing code. So we know to sub-millisecond precision when that fireball started lighting up the sky and when it finally went out. And from that, if we see a fireball across multiple locations, across multiple cameras, we're able to triangulate it. This was a fireball that seemed to drop a meteorite into Katipanda Lake Air. So a team went out to search this salt lake, again, white, salt, black rock, and successfully recovered the Marili meteorite, which was sort of like an early proof of concept of the power of these camera networks and these large area, sort of off-the-shelf networks to be able to recover meteorites with orbits. The success of that allowed that to go global. So, and then I was then moved to the UK and was fortunate enough to be part of setting up the UKFAll network arm of that. So the idea is then to set up this camera network in the UK to find meteorites. Now Australia has a lot of good things going for it. Red desert, black rock, very easy to find meteorites. Also, the theory goes. UK, very different. Dark green deciduous forests, muddy bogs, little black rock, very easy to lose it. However, we took hope that we have precedent in the UK for finding meteorites. So the last one in Scotland was over 100 years ago, so quite a while, but we have found them in Scotland. The Strathmore meteorite fell on the 3rd of December 1917. It's an ordinary chondrite of a type L6. It was an air burst, so it blew up in the atmosphere and split into 4 fragments, one of which straight up nailed this woman's house. And what I really love about this story, I really love this GIF, but I love it for an extra reason, in that this meteorite fell. It did break into 4 pieces. One of those pieces did punch a hole through these poor people's house. However, at the time in 1917, it took several days for the News of the World to descend on Strathmore and figure out what had happened. And these people live in Scotland. It rains a lot. Having a hole in your roof, not a good idea. So they had fixed the hole by the time the News of the World got there. Not to be dissuaded, some journalists took it upon themselves to get their quill, take 2 pictures, and in the second picture, ink in the hole to sort of try and visualize what had happened. So yeah, it's one of the kind of first examples of fake news in the modern media, which I find quite entertaining. The most recent meteorite, the second most recent meteorite now that's been recovered in the UK was the Glasgow meteorite in 1991. It fell in a fellow called Arthur Pettifor's back garden. And the description he made of it was amazing, where he said, "Oh, I heard this whistling noise and then a disturbance in my conifer hedge, followed by a thud as he was tending to his onions. This meteorite literally landed right next to him." And what I then really enjoyed the rest of his description was saying he was felt very lucky that he didn't get hit by it, but was more alarmed that it narrowly missed his greenhouse. And as I've recently taken up gardening in lockdown and have a greenhouse myself, I completely empathize with those priorities. So meteorites in the UK, we have 18 official meteorite falls in the UK and 6 in Ireland. Over the last 200 years, we've recovered about 1 meteorite every 9 years. Which is like pretty good going for a place where it's very hard to find meteorites. However, we should get 2 or 3 meteorite falls land on an area the size of the UK every year. So we're basically batting way below our average. We're not finding many meteorites that we really should be able to. And so the aim of like the camera network, starting to set these camera networks up in the UK, is to start improving those numbers and recover more meteorites. So when I moved back to the UK in 2017, I started climbing out of roofs, out of windows onto roofs around stately homes and observatories, putting cameras and installing them on these sort of like very commanding views over the local landscape, setting them up 150 odd kilometers apart to help install the UKFAll network, which is basically using the exact same kit as the Australian Desert Fireball network. We currently have 6 or so cameras that are working autonomously up and down the UK at various sites. Again, using that kind of DSLR off-the-shelf 30-second exposure, De Bruijn sequence, fisheye lens to image fireballs. What a day and the night of one of our cameras looks like, so you get kind of an idea, is, as you can see, one of the big problems we have in the UK is cloud cover. Very few of our nights are clear for observing, so it's very kind of challenging to observe meteorites or fireballs or anything really. And becomes even doubly challenging when you have a very distributed network. So one camera might be clear, another camera might be cloudy. However, if we're lucky and there is a clear sky, we are starting to see beautiful stars, we're starting to see the planes, and also we do image beautiful fireballs across the UK from multiple stations. However, like I said, it's a very distributed network. But fortunately, we're not the only game in town. There is another camera network in the UK called SCAMP, or the System for Capture of Asteroid and Meteorite Paths. They have a slightly different approach. They're still after fireballs that drop meteorites, but they use a video camera with a fisheye lens, so it's like continuous footage. And they have several cameras up and down the country, one in Manchester, one in Cardiff, a few in other places. And like I said, they take video cameras. They are an extension, well, the same way the UK Fireball Network is an extension of the Global Fireball Observatory. The SCAMP network is an extension of the French FRAS network, which has over 200 cameras now across Europe, imaging fireballs across the continent. And what I really love, well, this is an amazing camera system. It gets some phenomenal data, but also absolutely sensational acronym game is upon us here. So FRIPON, if anyone's up on their French, means mischievous small child. And the name they chose for the UK network was SCAMP, which means a very similar thing. So just absolutely incredible acronym games there. They should be very proud of themselves, as well as doing sensational science. But it's not just kind of professional academic networks that are in on this game. There is also, so I say amateur astronomers, but amateur really does not give them credit. It does a disservice to the amazing science and insights they are able to obtain on a voluntary basis. So for example, the UK Meteor Observation Network uses CCTV camera narrow angle lenses and has several hundred cameras up and down the country, imaging different parts of the night sky. As does the Nematode Network, the Global Meteor Network, All Sky 7, all using a variety of different types of kit, from CCTV cameras to video to still images to Raspberry Pi cameras. And what is really lovely about these cameras is they're after a different thing. They still want to image fireballs that drop meteorites, but these are much more sensitive cameras. So they are able to capture and image meteors, the fainter, short-lived events. And they produce this absolutely stunning data set of meteor observations. And you can kind of see the hotspots across the night sky of where these different meteors are. And what I love about this is there are clearly meteor streams in here that we have not been discovered yet, which is really exciting and be really wonderful to eventually dig into this data to figure out what meteor streams are which, and are there any new ones that are new to science that you can basically get out of a voluntary network collecting absolutely stacks of data of meteor observations. Now, as you can kind of see, the UK is this kind of hotbed of meteor science. Lots of both citizen scientists and academics setting up camera networks. And you might be thinking, well, hey, you've all got the same aim of wanting to image fireballs and collect meteorites. Why don't you all work together? And that's exactly what we did. We founded the UK Fireball Alliance, which brings together basically all the camera networks, all the camera operators, as well as anyone interested in meteor and meteorite science. So that's like all the museum curatorial facilities that might want to look after and curate any meteorites we find. And then all the academic institutions that want to go study any meteorites we find. And it's just really lovely sort of collaboration across citizen science, across academia, international, diverse, the works. And credit goes to Jim Rowe for basically bringing us all together, getting us all in a room, and sort of putting together the framework by which we could share data efficiently, quickly, because we're all collecting data using wildly different systems, wildly different components and software, producing very different outputs. And we've now developed together this kind of unified meteor reporting sort of framework where it can go into any model, any sort of trajectory analysis, any dark flight to figure out if a meteorite survived and where it landed, which is sensational. And then what's great is then we have 7 times more eyes on the sky when we're all working together. And while the north of England and Scotland is still a bit sparse and we're wanting to improve that, we've got really dense coverage over the south of the UK and Wales. And so the scene was set. The idea was going to be, okay, we'll collect all this data, we'll see this fireball from multiple stations, from multiple different networks, we'll share that data, and then if it drops a meteorite, we can go out and collect it. 28th of February 2021, the UK Meteor Observation Network saw this and also captured this video. Several others are available just before 10 o'clock at night. The Fripon network, the UKFAll network, All Sky 7, Nematode, every single camera network captured this event. It was a sort of very lucky, clear night across the UK. We captured it on no less than 16 observatories. And also, because it was such a clear night and it was relatively early at night, loads of people saw this thing. So it was seen by over 1,000 people up and down the country, as far south as the north of France, as far east as Norway, up in Scotland and across in Ireland, saw this fireball event. And the modeling sort of suggested that some material, maybe a few hundred grams, had survived to the ground. And the sort of landing area was centered over the little town in the Cotswolds called Winchcombe. Now, you may notice the date was 2021. We were in peak lockdown. We couldn't go anywhere. We weren't allowed outside 5 miles away from our house. So obviously, while there are meteorites in the ground and all that, that's all very exciting, we couldn't get a team out there just yet. So my friend Ashley King and various other people got on the news to tell people that we think there's a meteorite on the ground in Gloucestershire. Maybe if you're on your one daily allowed outing, if you see any little black rocks that weren't there yesterday or where they shouldn't be, please let us know. And then no less than 12 hours later, we get sent this image of the now famous splat, which is basically what happens when a very delicate meteorite impacts very quickly with a driveway of the Wilcock family in Winchcombe. Narrowly missed 3 guinea pigs who immediately identified it as a very rare type of carbonaceous chondrite. And then because they had seen the news reports about this, they sort of had been told by that how to collect it safely. They did absolutely everything right, collecting it with gloves into sterile bags, using aluminium foil, not using a magnet, and got it out of Earth's environment within 12 hours. So it's incredibly well preserved. My colleague Richard Greenwood was able to get permission to go out there the next day to confirm that it was a meteorite. And then that left us with this conundrum. We're still in lockdown, but we have a meteorite on the ground. It seems to be a very rare type of meteorite. And we know that fireball fragmented in the atmosphere based on the fireball data and the fireball images. So there are likely more fragments elsewhere in the area. So we then tried to seek permission to go to Winchcombe to search for more fragments through our work, and filled out a literal mountain of paperwork and risk assessments to get institutional sign-off to get to the area in a COVID-safe way. We were able to do that, get a very small team down into the Winchcombe area to start searching for this thing. And luckily, meteorite searching is basically a socially distanced activity. You line up 2 to 3 meters apart, walk across the landscape, scanning the ground in front of you for little black objects in the hope of finding a meteorite. This carries on a lot. We searched for 5 to 6 days. At the end of day 5, we still hadn't found anything. Well, I say we haven't found anything. We'd found loads of things that weren't meteorites, because bizarrely, there are a load of things in the UK countryside that look an awful lot like a shiny black rock that aren't. For example, sheep poo is a dead ringer for the meteorite fusion crust. And I'll give a little bit of a spoiler alert. The image on the right is a sheep poo. The image on the left is a meteorite. Can you spot the difference? It's very, very challenging just from a distance. So you have to kind of individually check each and every one. And the kind of key thing is flies don't go anywhere near meteorites. They like the sheep poo more. But then my partner, Mira Ehaz, diligently on the Saturday, after many other people had gone home, was very, very lucky and very, very diligent, spotted out the corner of her eye this shiny, glinty black thing in the ground, which is now the largest intact fragment of the Winchcombe meteorite. Much rejoicing ensues as she calls us over to kind of confirm that it was a meteorite. That's my friend Anya screaming in the background with excitement. And So yeah, we found this little black rock in the middle of a sheep field, very carefully picked it out of the dirt. It embedded itself 5 or 6 centimeters down. And what's really nice about this whole experience is it shows the system works, and much celebrating was had afterwards. So now we have this beautiful meteorite. So we started to tell the world about it, and you may have seen it on the news. It produced quite a storm. That we found the first meteorite in the UK. I really like this from the private eye, sort of referencing all our complaints about getting confused about sheep poo, and everyone thinking they'd found a meteorite when in fact they hadn't. And what was also really lucky about this whole thing is the people whose land it fell on very, very generously donated the vast majority of it to the Natural History Museum to curate and for science, because it's incredibly valuable for science that we got this meteorite and got it so quickly, and we have its orbit. So that was amazing. So most of the material is at the museum. The piece that Mira E has found is on display at the Natural History Museum in the vault, and I've been told very soon the driveway will soon be joining it, as they got permission to drill out the drive of the Wilcox Drive where the splat fell, and that's going to be on display as well in the near future, which is a kind of wonderful science story showing that kind of thing. The curators did an absolutely sensational job. If you kind of go back to the splat, you can see it kind of shattered into several thousand pieces, and they very diligently curated and marked and signposted every single one, where it fell, when it fell, when it was collected. An absolutely titanic effort of curation. They even kept the yogurt pots and the paraphernalia that the Wilcox family had used to diligently collect the material. So if you ever want to find a meteorite, Waitrose essentials bags and yogurt pots are the way to go. And so now we have this wonderful new meteorite, and it's loads of firsts. It's the first meteorite to be recovered in the UK for 30 years. It's the first meteorite where we've seen it fall, and so we have its orbit. And it's the first ever carbonaceous chondrite recovered in the UK, and that's a very rare type of meteorite. And because the Wilcox family found it so quickly and packaged it up and took it out of Earth's environment so quickly, it is complementary to and rivals the material brought back by asteroid sample return missions, where they're bringing material back from asteroids where we've gone to visit them. So this really is kind of the UK's first asteroid sample return mission, done for a fraction of the price, as we just wait for space rocks to fall out on us and then go recover them. I'd now like to go a little bit through some of the science, because the first few papers have started to come out about what scientific insights we've been able to get from this meteorite. This was, again, a huge titanic effort, but it started very simply. We need to weigh it first, and this was us in our hotel room. Didn't have any scales. We were trying to guess how big the piece that fell in the field was. It was heavier than a Kinder Bueno in the line bar. It was about 150 grams all told in the end. The next kind of analysis that's very important is the oxygen isotope analysis. That's done at the Open University, and that was done within 2 days of it landing, which was insanely fast. So we already learning things while we were still in the field looking for the rest of it, which was amazing. So, like I said, the first paper that came out was published in Science Advances. It was co-wrote by myself and Ashley King. And as you can see, this was an extraordinary collaboration with international partners, academics up and down the country, curation facilities, citizen scientists, all the camera operators, all the searchers, all the finders, all the landowners were involved in this. There's about 40 different institutions. It was a huge effort to get this together. And then following that, we split into, as we said, this basically is like the UK's first asteroid sample return mission. So let's treat it like an asteroid sample return mission. And what teams like NASA and the Japanese Space Agency do is they split into crack teams focusing on different aspects. So I led the fine grain team looking at all the tiny materials. There was also a team looking at the coarse grain stuff, the organic material, the noble gases, the volatile content. If you can it has a paleomagnetic signature, documenting how it was curated and recovered, and what the fireball looked like and what that can tell us. And we've sort of been collectively in the UK Fireball Alliance. We refer to everyone who does fireball modeling and meteor science as wizards. because the maths they do is absolutely extraordinary and way beyond any of the rest of us. So I mentioned those oxygen isotopes. They're really important to classify meteorites. We classify them based on the ratio of oxygen 17, oxygen 18, and oxygen 16 isotopes. And basically, Winchcombe, which is these little heart-shaped data points, sits right in the middle of the CM chondrite field. And the CM chondrites are basically carbonaceous chondrites of the type Mahegi. And they are really, really interesting rocks. They formed 4.5 billion years ago, and almost nothing happened to them since then. But they're incredibly water rich. They're 15% water and have been extensively altered to clay. They also contain a lot of organic material in the form of organic molecules, but also carbonates, diamonds, etc., to 2 to 3%. And going back to one of the key questions we have about our Earth is, where did it get its water and where did it get its organic material from if it was a hot, dry environment in the early solar system? One key idea is you throw carbonaceous chondrite meteorites like Winchcombe early in our solar system at the Earth to deliver our oceans. So Winchcombe is a really good opportunity because we got it so quickly to study this kind of thing and answer some of these fundamental questions. When we cut it up and we start shooting it with electrons and lightning and lasers, what do we see? This is an element map where we've highlighted iron in green, calcium in blue, and magnesium in red. Magnesium, the red dots, basically show where all the anhydrous, the dry silicate minerals are, like olivine. The calcium map shows where all the carbonate minerals, basically like limestone. And the iron shows where all the clay is, which is kind of that stuff in between. But you can kind of see there's also some interesting objects in there. There's these round things in the sort of middle. They're called chondrules. They're the solar system's first lavas. They're basically, if you flash melt a ball of dust, it produces a melt and then solidifies. We also have these incredibly altered calcium aluminium rich inclusions, or CAIs. They are literally the oldest solid material in our solar system. They condense at very high temperatures, very close to the sun, just as it starts to shine. So they define the age of our solar system at 4.567 billion years ago. But you'll also notice in here that it doesn't all look the same. There are different regions in here. Like this looks like it's almost an entirely different rock. And at the time of counting, my colleague Martin Suttle's work published recently in Meteors and Planetary Science shows there are 9 different rocks in this rock. They're all CM meteorites of different types, but they have different textures, different geochemistry, different mineralogy. And what this tells us is this poor asteroid was formed, experienced some water alteration, was disrupted and reaccreted, and potentially disrupted and reaccreted many times. So it's this rubble pile, which very much matches what we see in the sort of asteroids that are visited by sample return missions. Some of the work that I was doing was showing how this fluid alteration has affected this meteorite, and it seems to be wildly heterogeneous. There are minerals in this, like these olivine grains, that if you put fluid next to them for a couple of days, they'll be completely altered to clay. But they are right next to a whole bunch of clay. So clearly water was in the system. Clearly there'd been a lot of fluid moving around here, but for some reason wasn't affecting the olivine. Even though right next to it, there could have been a relic grain of olivine that had been completely replaced to clay. So this is very kind of confusing about how we reconcile this in our understanding of how fluids are affecting these asteroids. My colleague Anya O'Brien and Lydia Hallis have been doing some really cool work looking at the organic components in the Winchcombe meteorite. So the left-hand 2 columns are Winchcombe organics. The right-hand 2 columns are the soil samples we collected around where the Winchcombe meteorite fell. And basically red means they have identified a specific molecule and it's in high abundance. Blue means they haven't identified that molecule. So in the top, you can see there's a whole load of organic material in the Winchcombe meteorite that isn't in the soil, which is great because that means that is extraterrestrial. But there's also a bunch of organic material in the soil that isn't in the Winchcombe meteorite. So that's great as well, because that means that the organic material hasn't fully contaminated the Winchcombe meteorite, because organic contamination can happen in a matter of days or even hours. So it's very good that we don't seem to have much organic contamination. However, that's not to say this meteorite is completely pristine and completely unaltered. One of our PhD students at Glasgow, Laura Jenkins, has done some really diligent work showing these new secondary terrestrial phases are forming in the samples that were recovered maybe 6 days after the fall. So that 6 days, even though no rainfall fell on this, was enough to grow carbonate minerals in the fusion crust cracks, or grow calcium sulfates on the surface, or have salt crystals growing out of the rock at you, which shows the importance of recovering these things really quickly, using the camera networks and using citizen scientists to collect these samples very, very fast, as soon as possible, so they don't get affected by Earth's environment. One of the really cool results we had was the bulk hydrogen. So basically, we measured the water component, the water content, and the isotope ratio of the water in the Winchcombe meteorite. And again, one idea is these CM meteorites could be a significant component to Earth's water budget. But one kind of caveat is when we measure CM meteorites, they look a lot like Earth's oceans. But do they look like Earth's oceans because they have been altered by Earth's environment and sort of equilibrated with it, and that's why they look like the Earth, or are they actually like the Earth to start with? And because we got the Winchcombe meteorite within 12 hours, it took it out of Earth's atmosphere, mitigated the possibility of it altering, and it still looks like the Earth, so it's still a very close match to Earth's ocean composition. That is a very good sign that shows that CM chondrites might be a significant contributor to the oceans and rain that we see on Earth today. The Fireball, the wizards, as we like to call them, have also done some sensational work looking at the Fireball, pulling apart the data. And Winchcombe seems to be a really, really lucky rock. There are only 4 or 5 other carbonaceous chondrite meteorites that have fallen and that we found. And most of them are like a couple of tons in weight when they hit the top of the atmosphere. They're really weak, they break up loads, and most of it burns up, but you might be lucky to get a few 100 grams on the ground. Winchcombe started off at 66 kilos when it hit the top of the atmosphere. It's like a basketball sized. And it came in at just the right angle, at just the right speed, that it never experienced the pressure that would completely disrupt it. So only 500 grams survived to the ground, but none of it should have survived based on what we understand. So it shows that tiny, tiny objects can survive atmospheric entry, which is really interesting. It's also starting to show us where carbonaceous chondrites might be coming from and might be being delivered from in our solar system, as it seems to have some links in terms of its orbital parameters with some of the other carbonaceous chondrite meteorites that we've imaged and seen fall, which is really cool. So what I really kind of like about all this is it really shows the power of collaboration, citizen science, everyone working together to build something that's bigger than its constituent parts. And I think Richard Iowadi on Have I Got News For You said it best. And so this kind of, yeah, hope everyone heard that. I hope the sound actually works. But yeah, what he basically said was UKFAll Alliance is a heck of an alliance. And it's really wonderful to kind of be a part of, to sort of do this collaboration and yeah, be as lucky as we were to find this very pristine meteorite after all our hard work. And hopefully this is not the end of that story. That's just the beginning of that story, because as technology is getting better, we are able to image the night sky in different ways, and doorbell cameras and your phone is equally able to collect really awesome images. So this is a Fireball which was taken by my dad over at local cricket club, and this Fireball, I'll let that video go again. And this Fireball was actually predicted to fall. So we saw the asteroid, the meteoroid, before it hit the Earth's atmosphere by some telescopes. And so we were able to point our cameras in the right direction to see this thing. Unfortunately, all our professional dedicated cameras that we've installed carefully over the last 5 or 6 years were cloudy. So one of the few images of this was my dad at the cricket club and the Brighton and Hove police force out on Brighton Beach. But what was really cool is other cameras like the Fripon network saw it, and we were able to recover that meteorite that fell in France. And in fact, that coincided with 3 other meteorites. So we had a situation, we had 3 meteorites and 3 Fireballs in 3 days. So on the 13th of February, Fireball was observed in France that resulted in a meteorite. That's the one my dad imaged. February 14th in Italy, meteorite was recovered. And February 15th in Texas, meteorite was recovered. I don't think these events are correlated. They're just kind of random chance. They're all within a few days of each other. Their orbits seem to be quite different. But shows that more and more we're able to recover meteorites with orbits using camera networks and utilizing citizen scientists. One really cool thing is we're starting to address that where do meteorites come from question by tacking those orbits back into space. And one of the greatest examples of this was the Motopi-Pan howardite meteorite fell in Africa. It was again one of those things where a telescope picked up the meteoroid in space a few days before it impacted the atmosphere. We were able to get cameras, well, I say we, other people were able to get cameras into the area to observe it, and were able to triangulate it and figure out where it landed. It turned out to be a meteorite called a howardite, and now we're pretty sure that the howardite meteorites come from the asteroid Vesta, but proving that is very challenging because we don't have samples of Vesta. But when we were able to sort of calculate the orbit and triangulate it back, the orbit takes it very, very close to Vesta. So there's sort of very strong evidence that these howardite meteorites are actually samples of one of the largest asteroids in the asteroid belt. I mentioned that sort of your phones have the capability to fireball track. If you don't know the fireball's coming, you can use this app called Fireballs in the Sky to report that fireball afterwards. And believe it or not, the inbuilt gyrometer of your phones is sufficient enough to accurately help us triangulate fireballs. So basically what you do is you open the app after you've seen it, point it at the sky where you saw the fireball start, click start, where the fireball went out, click end, tell us how long it lasted, what color it was, did it fragment, etc. And that data can then be built into and used in modeling where this fireball might have gone, and if indeed any meteorites are on the ground. So it's free, would encourage you to download it. There are other meteor reporting sites available, but also you can also if you want to get involved, feel free to reach out. I know particularly the networks like UK Meteor Observation Network or UKMON, Nematode, Global Meteor Network, All Sky 7 are always looking for new people to purchase cameras or install cameras, so we get more and more eyes on the sky. UKFAll Network and SCAMP are always looking for new locations, so we have the challenge of we need to fund the money through grants to be able to purchase new cameras to install them, and it's a more distributed network. But yeah, feel free to reach out to us or any of the sort of people involved if you're interested in having a fireball camera on your roof, like I said, particularly UKMON and Nematode, or you can sign up to our newsletter for the UK Fireball Alliance to keep in touch with us and what we're doing. And I think with that, I don't know how long I've waffled for, but I'd be more than happy to take any questions. And thanks very much for having me.
Yeah, thanks, Luke. There are a couple of questions in the chat that came in. How do we know 50,000 tons fall to Earth? How's that determined?
Yeah, really good question. Several ways. So one way that's kind of brute force is you go to Antarctica, you dig out a huge, like several tons of ice, and you melt it all. So you know, basically know the volume, you know how long that ice took to form, and you basically weigh all the cosmic dust that's in it. And then go, okay, this is how much cosmic dust we have in this area, multiply that up over the size of the planet, and that's your flux rate. There is also stuff you can do for longer time periods, like measure ocean soil. So basically like the ooze that rains out, some of that is cosmic dust that builds up over a long period of time, and cosmic dust is preserved in that, so you can kind of get an idea about how much dust is falling over sort of thousands of years or millions of years. And what we're starting to be able to do is get meteor databases that are big enough, like the UKMON database is probably getting to the size where you could start making an estimate of this is, okay, how much material is falling right now into and over the UK, and therefore extend that across the planet. So yeah, lots of different ways to guesstimate or estimate how much material hits the top of our atmosphere every year. But it's a lot, surprisingly a lot, but it's also a very big planet. So
there's a question from AC. AC, you're always with us, and I have to apologize. I don't actually know your name other than AC. can you unmute and present your question? Is AC still with us? The question is about amino acid composition. Ah, yes.
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 Hello. Okay. Actually, my initials are AC, but my first name is Adrian. Adrian. Yes. Sorry. So the question basically is, I'm actually a molecular biologist, and I'm very interested in exobiology and origins of life. And one of the wonderful things about biology is that, and I'm sure some of you are probably aware of it, it's that the amino acids that compose our proteins have two different forms. It's called the chiral asymmetry, which is the same thing as the left and right hand. So it's that kind of similarity. And we're all composed of one of those forms, which is the left-handed sort of version of these amino acids. And so one of the questions is to how did that arise? You know, why did life pick the left-handed amino acids and not the right-handed amino acids? And there have been some determinations in meteorites that even though these amino acids are synthesized in space, and usually in the chemistry, you would form both types at the same ratio of both left and right-handed, but that perhaps it's actually the destruction of one of these handed forms preferentially that added this asymmetry of abundance of one of these amino acids, which somehow life incorporated in that form. So I was just curious, and some of that analysis has been done on meteorites and shown that there does exist some of this asymmetry. So I was just curious in the meteorite fall that you mentioned, if one of those analyses had been performed and if that had perhaps been published.
Yeah, so there is a study that's out right now by Queenie Chen of Royal Holloway, looking at the amino acids. They detected a whole bunch of them, which is really cool. I don't recall there being any asymmetry. I think it was all pretty symmetrical, so like equal amounts of left-handed and right-handed amino acids. But yeah, it's talking about building blocks of life, these carbonaceous chondrites, particularly CM, seem to be chock full of amino acids. So it's like everything you want to seed a planet with to give it the opportunity for life to emerge. Again, I'm not a molecular biologist. I don't know how we get the chirality in there. That's a really interesting question. But yeah, so I think from memory, Winchcombe is symmetric, and a lot of meteorites are symmetric. There isn't a bias one way or the other.
There have been some analysis that show some bias, not fully, but there has been some. And again, the thought is that perhaps there's some mechanism, and some theories involve cosmic rays that preferentially destroy one form or the other. Also, some of the building blocks of DNA are also found in meteorites, the nucleic acids or precursors to that. So those are also found there. So, as you said, almost all the ingredients for the soup are there. Well, thank you. It's a fantastic presentation. Really excellent job. Thank you.
Thank you very much. Yeah, I was going to say on that note, if we ever found a meteorite that was only one chiral, it'd be like smoking for life somewhere else.
That would be something like close to Nobel Prize winning discovery.
But not yet.
No.
I saw a question from Kevin. What role do you see, if any, for the radio meteor scatter observations? And maybe Brian has already had some discussions with Fireball Alliance on this. So feel free to chip in, Brian.
It's a fantastic question, and I believe it's already starting to be done in certain places. I can't think of a specific example off the top of my head, but yes, what's wonderful about meteors is you can track it. With radio, you can track it not just as it's coming through the atmosphere and burning up and the bright thing that we see, it's as it's coming down as well. Same with radar. So one of the big problems we have in optical meteor science is we lose it at about 30 kilometers height, and then we have to have a very good wind model to figure out where it's going to land. And if we have more constraints on the way down, that would be wonderful. So yeah, again, like I say, I'm the rock doctor. I look at the meteorites when they land. The wizards do all the modeling, but yeah, I'm sure there is a place in the pipeline for building in radio astronomy as well, because it sees something that we can't see with the optical stuff.
Are there places on Earth where more meteorites fall than others due to optical magic considerations?
Some people like to think so. I think probably not.
Okay.
There might be some consideration, like, like if Earth's orbit is slightly inclined. So if we're coming down through the ecliptic plane, we might get more on the southern hemisphere as we're going through, but then on the way back up, we get more on the northern hemisphere. We think on average it would balance out to be approximately random. But there are interesting things of like concentrations of meteorites in certain places, but they typically tend to be, that's where meteorites are concentrated because they don't get affected as much by Earth's weathering, like hot deserts and cold deserts, or there is a socioeconomic bias towards it. So there is a wonderful correlation between meteorite finds in Africa and the border with Morocco. So more meteorites are found in Morocco, in the sort of African continent, than anywhere else in Africa. And that is basically because that is the only place where if you find a meteorite, you own it and you can sell it. And people have realized they're worth quite a bit of money on the black market of meteorites, which is also a thing that exists. So all the nomadic tribes have got very good at identifying meteorites. Like, they're like the premier meteorite hunters. And they go around finding all these little black rocks, take them to Morocco, drop them on the ground, take a picture with a GPS and say, I found this meteorite in Morocco, and then they can sell it on. So there's loads of meteorites that come out of Morocco, but almost all of them weren't found there originally, but we can't tell where they were.
Is the fall of iron meteorites affected or steered by the Earth's magnetic field? Andrew Thomas asked.
That's a really good question. So obviously there would be some effect, but whether it would actually change its trajectory or not, like, so obviously it's magnetic, it's passing through a magnetic field, there will be some impact, but is that enough impact to counterbalance it being just really quick and like the sort of like orbital dynamics of it, the gravitational effect of it? So I think any effect would be so minuscule that it wouldn't really make a difference to its ultimate trajectory.
I guess it has quite a lot of kinetic energy.
Yeah, these things are clopping in at like 20 kilometers a second.
And another question from Adrian. Have any meteorite orbits been determined to be of interstellar origin?
There was a few meteorite fireballs that we saw that everyone got very excited about because they were initially had enough escape velocity to get out of our solar system, so interstellar objects. But as you built in more and more observations and more data came in, that just got more and more refined and eventually brought it into the Trojan Jupiter family comets, basically, which would still be really cool to go collect, but sadly we didn't find that one. But everyone got very excited about, okay, we need to go because this could be an interstellar object. But yeah, like I said, eventually it'll be a matter of time before we start seeing those in our data with these incredibly hyperbolic orbits or with enough momentum to escape the solar system's gravitational well. So could be soon. I will say though, we do in the meteorite record, in certain carbonaceous chondrites and certain chondrites, we don't have interstellar meteorites so far as we know, but we do have grains inside them that formed in different solar systems, which we call pre-solar grains. So they're these tiny little diamonds, silicon carbides, that formed during the death of a supernova, formed during the death of an asymptotic giant branch star. That material condensed, and then that went into the giant molecular cloud that ultimately formed our solar system. And through random happenstance, somehow some of those grains survived the turbulent environment of solar system formation, are preserved in the meteorite record. So there are lots of groups of people that study these pre-solar grains to understand galactic stellar evolution. So we do have bits of other solar systems in the meteorite record, but no interstellar meteorites so far as we know yet.
Are there any more questions? If so, just unmute yourself and...
Yes, thank you. Yeah, Luke, question, if I may.
Yeah.
Yeah, when Apollo went to the moon, they brought back samples and they estimate the 3.8 date. Yeah. Right. They now
For the late heavy bombardment.
yeah, they now
Yeah.
believe that they actually collected samples of ejecta from Tycho. So, and I might be putting them on the spot, but like to hazard a guess at how old? If the ejector was what they brought back, any idea on the age it might actually be?
So yeah, so this is all really interesting stuff. So like the Apollo samples,
Yeah.
basically suggest that there's a 3.8, 3.9 billion year hard reset on the lunar surface. So
Yeah.
everything before that got destroyed. And that's the idea, is you have this late flux of asteroidal material or cometary material, potentially destabilized by Jupiter throwing a bit of a wobbler, turning the inner solar system into a pinball machine. However, yeah, there's recent modeling has showed that maybe what that date isn't the date of Imbrium, it's the date of something else, or the date of Tycho, or and there's a mission I think going to be going soon to the South Polar Aitken Basin, which is one of the biggest impact structures on the moon. And if we get a nailed on date for that, that will be either the nail in the coffin of that theory and it will die, or it will be the proof. What's interesting though with that theory is we've started to look on other bodies, like we've got these really old Martian meteorites that have grains inside them that are like 4.4, 4.3 billion years old, show no evidence for late heavy bombardment. We have bits of Vesta that show no evidence for late heavy bombardment. There is very limited evidence for late heavy bombardment on the Earth. And so that whole theory has come out from this one data point from the Apollo samples, which if it's dating one crater or a different crater, we get a very different interpretation. And it might just be, we don't need Jupiter to do anything. It's just a slow decay of the impact rate naturally over time, which is what you would kind of expect if nothing else happened. So yeah, we could be seeing the death of that theory, sadly. I kind of like it because it's kind of cool, but
So do I, but you never know. But say, would I hazard a guess? An age?
Of the late of the
8, yes.
Oh, I'd say probably the biggest bombardment would probably happen at 4.4. If it's just a steady decline. So the biggest flux of impactors would be when you get what we call the late veneer, so the last 10% of Earth's mass, which we think was mostly carbonaceous chondrites. So basically it's not just like you're impacting a planet, you're adding 10% of its mass to it. No, sorry, 1% of its mass to it. So yeah, that would be a pretty rough time, but I think that happens around 4.4. So if late heavy bombardment goes away, those craters are older.
Yeah, I know because when they plan to return, they're going to go and try and go to the equatorial region of the moon to try and get some more data for the dating.
Yeah, absolutely, yeah, and clear cut samples where it's like it's not ambiguous where it's come from.
Yes.
Yeah.
Thank you.
Send some geologists up there again.
Well, buy a ticket.
Yeah.
Thank you.
Yeah, Elon will take you. Something I was quite interested in myself, but Sajid has asked a question about the timing pulses on the cameras. Can you just unpack that a little bit?
Yeah. So again, I'm not the guy that did this. Very much cleverer people than me are the people that came up with this idea. So, like I said, other camera networks have gone different ways, like using video. And so then you don't need the timing sequence because you just go frame by frame and you've got that embedded into the video. With our thing, we wanted a still image because then we get better exposure, we get more stars, we can calibrate our images better. But it's that 30-second gap of time that we want better precision on to get a decent triangulation, because that's a huge amount of time in the length of time of a fireball. So basically what our kind of the people who designed the cameras did is they put a liquid crystal shutter between the detector and the lens, and that goes opaque and clear along what's called a de Bruijn sequence, which is it's the shortest non-repeating sequence you can have in a given time frame. So if you get more than basically 4 dashes, so opaque, clear with any object, you can figure out when it came clear as a unique combination of long and short dashes that is in that image. So basically a fireball moving at 20 kilometers a second slowing down will be zipping across that image very, very quickly. And so the opaque on-off of this liquid crystal shutter will chop that fireball into bright and dark segments. And so we can start then figuring out when it hit the image, when it started in the image and when it finished in the image. And yeah, it seems to be quite an effective way of figuring out fireball timings from a 30-second exposure. Does that answer the question? Again, I'm conscious I'm not the person that designed this, so I'm kind of trying to explain it secondhand.
That's with reference to the start of the frame, is it?
Yes, yeah. So the GPS goes, okay, we've opened the shutter, and then the de Bruijn sequence starts, and then shuts off. We have had some annoying things with our downtime. So like the Frippon cameras, they're imaging the whole time. We have like it's 28 seconds exposure, then 2 seconds of saving the image. We've had so many fireballs finish in those 2 seconds, you would not believe.
Oh, there's another question from Adrian.
That's a good question. Any samples from the Theia impact will ever be found? Very good question. Very interesting. My hunch is, how would you know? Because it would look like the Earth. So you'd have a rock that, for all intents and purposes, looks like planet Earth. And your assumption would have to be that it had this little journey in between where it went out and in again. If there's any surviving stuff from that, so I mean, I'm pretty sure from the Theia impact, most of the upper mantle, like from basically to most of the upper mantle, completely melts, and the entirety of the moon melts. There's not much solid material there that isn't like, the Earth's core, which didn't get exposed. So yeah, I think it'd be very hard to have any solid objects left. Everything that fell down would basically fall into a magma ocean and remelt and rehomogenize. You might be lucky and get certain minerals that are really robust, like zircon. Basically, you can do almost anything to zircon and like cook it up to several thousand degrees, it won't melt. Smash it really hard at like 80 gigapascals, it might change phase or produce some microstructures, but that might be the only evidence you might get surviving for the Theia impact. I think most of the evidence in and around that is that we're so chemically similar, and it's very dynamically hard to get a moon that big in that close orbit without a giant impact. So say if you had some zircons in a very, very old rock, and they were, what would be 4.4 something billion years to coincide with the Theia impact, or no, 4.5 something. If you had zircons like that are shocked to hell and saw like some really extreme pressures, then maybe you could argue that they might be evidence for that. But as far as I'm aware, those haven't been found yet.
Thank you. Yeah, that was, as comments in the chat have said, that was just so incredible. Thank you very much, Luke.
Thanks very much, and thanks for having me.
That was great. And continuing our theme of meteors, I'd like to give Brian some time. You should be able to share your screen if you want to, Brian. Over to you.
Yes, well, very good evening. And first of all, thanks, Luke. That was a fantastic talk, really great stuff. A couple of matters arising from the questions there. the radio project has only just started to talk with the UKFAll fraternity following an introduction by Paul to Ashley King at the Natural History Museum, and I have an outstanding presentation to do to Peter Campbell-Burns of UKFAll. He's away on holiday at the moment, so we're right at the start of discovering how we might collaborate, and the project itself, well, I'll describe that to you now as quickly as I can, because I know you've been I don't know how much concentration people have got left after such an excellent talk. Here we go. Hopefully you can see this. Some of you may have seen it before. Nearly a year ago, we installed the UK's first amateur-operated meteor beacon at the Sherwood Observatory of the Mansfield and Sutton Astronomical Society, which is as central a location as we were able to find for the beacon. It's been operating cheerfully since then, so nearly a year's operation. There's the box that powers it. The antenna points vertically upwards to illuminate a piece of sky above its location near Mansfield, about 400 to 500 kilometers in diameter at the altitude of 100 kilometers, where meteors burn up and create an ionized trail that we can reflect our signals off. And it's worth pointing out that with the type of approach that we're taking, it is only while they are burning up that we're able to actually do anything about tracking the meteors. Once they've stopped ablating, and if there's any debris coming down, we've lost them. But we may be able to work out some useful trajectory information. I'll come to that in a minute. If anybody's interested in looking at the status of the beacon, if you go to the beacon website, ukmeteorbeacon.org, you find the status page. It will show you the power it's running and certain other parameters, what the temperature is and whether everything's working okay. So the beacon illuminates this region above it, as I say, with a diameter of about 400 or 500 kilometers. Echoes off meteor trails can be received out to a distance of something like 1,000 to 1,200 kilometers. If you're much closer, then you will also get echoes of aircraft. So you'll see lots of aircraft echoes in the presentation that I'm showing you. This is the kind of thing that the echoes look like as conventionally observed. The Brands project in Belgium has done a lot of this, and a lot of people have monitored these echoes. And these very horizontal little lines here are from meteors burning up. They're probably no bigger than grains of sand, but they leave an ionized trail that's big enough for us to get an echo off. And they exhibit very rapidly changing Doppler shift. This is what we call a waterfall display. You've got frequency across here. The upper display shows instantaneous amplitude. The lower display is a waterfall, so you've got time running down, and brightness or size of the echo is represented by brightness. These slowly changing Doppler shift traces here, those are aircraft. They're quite easy to identify. This kind of display doesn't show you much detail of meteor echoes, and what we're doing now using modern digital signal processing techniques means we can look at much more detail, and I hope I can bring that out here. Here's a fairly typical echo. The first bit is rather faint, but that is the head echo with the changing Doppler shift as the path between the transmitter, the meteor, and the receiver is changing as the meteor is traveling along and decelerating. We'll talk about that a lot more in a minute. The things that we're interested in are seeing the head echo. The tail echo is caused by ionization that's more or less static in the atmosphere. And if it's got any Doppler shift, it's due to the winds at that altitude. And I believe that meteorologists use these echoes to judge the speed at that sort of altitude, 80 to 100 kilometers, where they can't probe with radiosondes and they can't probe with satellites because they'd burn up. So just to explain again the details that I want to distinguish on meteor echoes, there's the head echo with the rapidly changing Doppler shift as it decelerates, and the path from the transmitter to the receiver via the meteor changes. So you see it starting to decelerate here, and then it appears to accelerate away. That's an optical illusion caused by the path, the geometry of the trace. And here it's left an ionized region that's continued to be reflective, in this case, for several seconds. So the head echo and tail echo. Now, to receive these, we're trying, the key objective of this project is to make it as approachable as possible by everyone and to develop STEM-based projects for schools and colleges. So you can receive these echoes with really quite simple equipment, a PC, a simple software-defined radio, and free software. Here is an example of a software-defined radio that works adequately and can be purchased on eBay for about £12. You'll find instructions on the website pointing you to designs for antennas made out of wire and plastic plumbing pipe, which can be made just for a few quid, and you can get meteor echoes with such a system. This is not terribly clear, possibly, but this is an echo of our beacon received on one of these £12 dongles. There are better ways of going. There's a thing called the FunCube dongle that some people will have heard of, which is a better solution. And there are lots of other software-defined radios, but we're standardizing on one from a company called SDR Play, and it's called the RSP-DX. The reason we're standardizing on it is it has features that we're using to enable us to observe with more precision, basically. So here's an example of a head echo of a meteor, which starts off with about a kilohertz of Doppler shift, which represents the path between the transmitter, the meteor, and the receiver, reducing at about 10,000 kilometers per hour. It decelerates down to the point where apparently it's hanging static in space. That's purely an optical illusion, and then it appears to accelerate away. That's as the geometry of the path's changing and the meteor is going away from you. In this case, about 400 hertz, so it appears to be going away at not far short of 5,000 kilometers per hour. And then it's the trace stops there because the ablation is reduced to a point where it's not producing sufficiently dense ionization to be reflective to radio. Of course, I should explain that the interest in doing this is that we can make our observations by day and by night and in all weathers, of course. And the objectives really were initially to provide a means of studying meteor events with much higher resolution than has been done with radio in the past, and to provide interesting STEM-type projects for schools and so forth, and provide a means of people to make observations of meteors and look perhaps at the different types of echoes that we see, and I'll show you quite a few different ones in a minute. And one of the interests of talking to the optical monitoring systems is to understand how our echoes and the types of echoes we see relate to the kinds of meteors, optical observations they're making. It would be very interesting, for example, to compare color information with the type of echoes we're receiving, and this all provides great opportunity for some amateur citizen science and observation. Our main science objectives can be found on the website. I won't go into great detail here, but there are almost as many as you care to think of yourself. Not everyone's going to be able to build their own receiving system. They may not have space for an antenna, or they may be in an electrically noisy environment, and of course, electrical noise is the bane of all radio astronomy. And so to that end, we are working towards phase 2 of the project, which is to design, build and deploy a number of web-based receivers. And this is the block diagram of the receiver that we're currently working on. We have funding from the RSGB, Radio Society of Great Britain, to build 3 of these and to deploy them. And we're hoping that when we've got the design stabilized, it will all be in the public domain. We hope other people will make their own receivers and bring them into the network. The key features here, interestingly, the optical guys using their timing system, there is a sort of parallel here. We have to take care of latency through our receiver system and across the internet. So we inject the timing signal right into the front end of the receiver along with the meteor echo. I'll show you this in a minute on a display. Basically, the system is based on a software-defined radio, the RSP-DX from SDR Play. They're about £200, I think. A Raspberry Pi, the usual Raspberry Pi finds its way into everything. There is a GPS frequency reference here to make sure that our frequency control is precise enough to make very precise Doppler measurements on the meteor. And to provide, there's a separate GPS receiver that generates the timing pulses that we're inputting to the receiver. The idea is that we will deploy a number of these receivers. They will ultimately talk via a central server. They will stream their data. The data will be in the form of something very similar to a WAV file. It'll be sort of audio bandwidth, probably around about 20 kilohertz of bandwidth, so not excessively huge amounts of data at that point, streamed to the central server. Ultimately, we will write software on, and that stream will be accessible to multiple users. They will just be able to log on, pick the receiver they want to monitor, and take the data as a continuous stream. The central server will look at these signals coming from the different receivers and will decide, it will have rolling buffers for each receiver so that if an event occurs, then it will store the data for maybe 5 or 10 seconds before the event and maybe a minute afterwards and save it as a file for us to work on later, because one of the ambitions, or there are a number of ambitions that involve detailed analysis of the echoes, and to do that in real time is probably not practical. And particularly, one of our ambitions is to be able to use Doppler information to triangulate the meteor's location and trajectory. This is, I emphasize, an ambition. We don't know that we can do it yet, and there are a number of things we have to discover first to see whether it's a practical possibility, and we're working in that direction now. This is what one of the receivers looks like with its lid off. In fact, this one, you can't see it, but there's a touchscreen display on it. Most of them will not have any display. There will be simple black boxes. The input for the 50 megahertz receiver, should have explained the beacon is on a 6 meter wavelength, 50 megahertz. It's operating in one of the amateur bands, and we have had to get, obviously, licensing for it from Ofcom and so on. This is the GPS receiver input. Over here is the connection to the network, and that's basically all the black boxes will have. Now, if you think about the Doppler shift on a given instant of a meteor, if it's at this time here, if you've got a receiver here, a transmitter here, at this time here, both paths are reducing, so you've got a positive Doppler shift. At the point, the midpoint here, you get a point where the Doppler reduces to 0, and then as it carries on, you get to a point where the Doppler shift is increasing. Now, if you think about trying to do the same with multiple receivers, and here's a simple two-dimensional analysis of the Doppler shift of a particular meteor measured from 3 receivers in this case. The transmitter is illuminating the meteor tail, its ionized tail, if you like, which is a kind of cylindrical structure of unknown length, which behaves like a wire when it comes to reflecting. While it's strongly ionized, it behaves more or less like a wire and will radiate like a wire. It's being illuminated with circular polarization. It will pick up the energy in the plane in which the cylinder is polarized, if you like, or the wire is polarized, and then reflect it to the receivers. And if you can, there are several points to try and get across here. Assuming that everything is equal, if we have an instant within a millisecond or so at which we know the trajectory or the Doppler shift for the meteor for each of these receive paths, if we have enough of them, it is felt that we should be able to calculate its trajectory. I hasten to add, I think this is an established technique with bistatic radar. I stand to be corrected. But the real problem with meteors is that the echoes are at this wavelength are polarized and they're directional. So not everybody is going to see them. So we therefore need quite a lot of receivers to be sure that we're going to see sufficient number of quality head echoes that we can analyze and work out the trajectory. So I emphasize that the calculation of trajectories is an ambition at this stage, but it looks as if it might be possible. This slide here shows the timing signals which are being input to the receiver, and in a similar way to the optical system, over a period of a minute, actually, we encrypt not just the time, but the date and various other information for the receiver. And the leading edge of each of these pulses, that's the bit at the bottom of each pulse, they're varying in length, you probably can't see it there to encode the data, but the leading edge is synchronized to UTC to within around about 100 microseconds. And bearing in mind that we're not dealing here with a radar system that's working with the time of flight of the radio signal, which would require nanosecond timing. We're dealing with measurement of the Doppler shift, and of course meteors travel at quite a few orders of magnitude slower than the speed of light, fortunately. So that's how we plan to see if we can do it. So there's many challenges to it, and we don't know whether we'll be able to overcome them. We are working on it. Now I'd like to just move on and show you what some of the echoes look like. We've been seeing, particularly, these are all very current ones taken around the time of the current lyrids, for example. Here's an interesting one. You see massive Doppler shift starts over there, although this is a very close scale here. We're only looking at plus or minus 100 hertz. And the two distinct regions of tail echoes that represent regions of the ionosphere that the meteors pass through that have got slightly different wind speeds. And you sometimes see some even weirder shapes. Here's one that looks as if it's gone through 3 regions. There's the head echo, you can just about make it out, and it stops there. And there are 3 separate tails indicating different wind speeds at that altitude. Here's a fairly typical shot that could happen, well, at least the upper part is fairly typical, type of thing that's going on virtually all the time. We're seeing on the system here, I would say, an average of 1 meteor ping per minute. There you tend to get more in the morning when we're facing into our direction of travel around the sun, but they're pretty random, and you sometimes see quite sustained occurrences, quite high frequency, sort of 2 or 3 a minute for hours. This morning was very busy, for example. And here you'll see another very weird shaped set of echoes, which we are interested to explore. There's another few echoes. And again, there's a lot of work needs to be done to decide exactly what's going on. Recently, I have been making observations simultaneously with both horizontally and vertically polarized antennas, and they see different, slightly different things. The polarization is pretty well random according to the track of the meteor. So sometimes the vertically polarized antenna will see a stronger echo. This one here, I think, is on the horizontal antenna. The vertical antenna saw the same echo, but not as strongly, and yet some of the other ones are stronger on the vertical rather than the horizontal. And this is more or less what you would expect when you're getting a reflection of a sort of wire-like reflector, which could make it appear to be directional, but that could be down to the polarization. But wire-like antennas also exhibit lobes and nulls, and in particular, if the meteor is traveling directly towards you or towards the transmitter, that will be in a deep null. If it's coming towards you as a receiver, you're unlikely to receive much a signal from it. If it's going towards the transmitter, the trail is unlikely to pick up enough energy to provide a reasonable echo in any direction. So hence the meteor echoes are directional and polarized, and hence the need for having more receivers dotted about than you would perhaps otherwise imagine. We possibly need 5 good measurements of Doppler at a particular instant before we can start doing triangulation, I'm guessing. Okay, I think that's basically enough. It would be very helpful to get various members of the radio astronomy community here in the UK getting out and about and putting up an antenna and showing us what they can do. There is a list of spectrograms on the website. It's not very fully developed at the moment, but you can go to the website and see some of the screenshots that we've taken. I have not been doing anything that could be remotely be described as systematic observation because I'm busy working on the hardware all the time. But when I hear a meteor ping go off, I leap across the bench and stab the screen capture button if I can get there in time. So that's the sort of level of observation I'm doing. But there are others out there, I'm sure, who could do a much better job. Okay, I think that's about it from me. It's possible that Tony Abbey might be around, and he, I think, may have some more images. But in the meantime, back to you, Paul, and any questions?
Yeah, thank you very much, Brian. Yes, that was interesting. Things are moving on at a fair rate. We'll get you back in a few months' time as the project unfolds. Does anybody have a question for Tony before Brian, before we conclude?
I can show you a little bit here. You can see my, if you see my camera, it's pointing at me receiving stuff from the beacon.
Ah, yes. How far are you from the beacon, Tony?
Well, that's the problem. And I've had a lot of interesting conversations with Brian about the fact that I'm only 40 miles from the beacon, you see, in Leicester. And I'm using a noise cancellation system to try and null out the carrier. Now, at the moment, if you can see my screen, it's not very successful. But the phase changes all the while where I'm trying to remove the direct carrier. And I've got, if you do allow me to share my screen, I've got a couple of images showing the setup I'm using. And as Brian said, I'm far too close to the beacon to actually do a useful job, but I'm trying hard.
Yeah, you can share your screen, but make it swift.
It will be, yes, okay. Share screen, right, okay. Right. Okay, Can you see that screen?
Yeah, yeah.
Yeah. Okay. Up on the left here, I'm using a noise cancelling system for 6 meter amateur band, and it takes input from the main antenna, which is a Moxon pointing at the sky, and then a sense antenna, which is at right angles to that, receiving the signals from the beacon directly. And we've got some variable phase shifters here, which are bits of coax in a box, and I can tune them and change the amplitude until in the combiner they remove the direct carrier. And this image here is forget the bucket in the background and all the other junk around, but basically that's the Moxon pointing at the sky, and then here is a dipole that's actually receiving the direct image from the Mansfield Observatory. Say those two signals going into this box enable me to try and cancel the main carrier. And then finally, more in keeping with what our main speaker was talking about, I also run a all sky camera all night, and it produces star trails, which I look at every few days, and you can see a couple of small meteors here. Obviously, there's the pole star.
The image hasn't
Tony,
changed.
we're still
Sorry?
looking at your circuit diagram.
Oh, can we not see this image? Oh, that's peculiar,
I
isn't
can
it?
see your mouse on the circuit diagram.
That's all you can see, is it? How weird. I've got 3 images on this same screen. Oh dear, I don't know.
Oh, they're probably in different windows. You have to reshare.
Okay. I'm sorry about this. Ooh. No. Oh.
I have to stop the screen share and then.
New share. Okay. Okay, I thought they were all on one screen. Okay.
Yeah, there we go.
Can you see this one, which is my star trails?
Yes.
Okay, so I'm collecting images all night, and there's a couple of meteors that are there. Let me just go. The thing I was trying to tell you about from the radio point of view was this one. Let me see if that works. Okay, can you see that one? Oh, it's got a green covering around it. Okay, that was my Moxon pointing at the sky, and then a dipole here collecting the direct carrier, and then using it to cancel in the 6 meter cancelling box. Okay, that's all I wanted to say. I'm only 40 miles from the observatory, and I can probably still do useful science. I'm not sure yet. It's TBD.
Yes. All right, stay in touch. Yeah, thanks very much, Tony, and thank you, Brian, and thank you very much, Luke. What a great evening. So that's it for tonight, and we'll see you again next month. And it's Thursday, not Friday. Do remember. I'll send a reminder. Take care. Good night, everybody.
Cheers, everybody.
Good night. Thanks very much. It was great.
Cheers.
All right. Thanks for having me.
Good night.